Welcome back to Physics 152 Online. We've seen in the double-slit experiment that there's a pattern of bright and dark fringes when it's viewed on a distant screen. But what if we want to get more quantitative? What if we want to find the actual function for the intensity or the brightness along the viewing screen as a function of the angle theta? Well, we can do this quite nicely using mathematics that we've already developed in our study of traveling waves. So as a simple model for understanding what the intensity of light will be at a particular point on the screen, let's model the light coming through each slit as a traveling wave and look at what happens to those traveling waves when they reach a common point on the screen, P, that's at an angle theta away from the horizontal. So the two traveling waves travel slightly different distances. x2 and x1 are the two different distances, and we see the familiar form for the two traveling waves. We assume that they have a common amplitude a, and so we know the identity for adding together two cosine functions gives us a product of a cosine function that only depends on position, and then a second cosine function that has the same form as a traveling wave. So this first term, including the 2a out in front, we can think of as a position-dependent amplitude. We will be able to show in just a minute that these distances, x2 and x1, depend on the angle at which the point on the screen is located. And so what we see is that this position-dependent amplitude will change and will have a different value at different points on the screen. And being a cosine function, it will go back and forth from 0 all the way to 1 and -1 and reach maximum values. So now we already know from our analysis of the double-slit experiment that that path difference, x2 minus x1, is indeed d sine theta. So it does depend on the angle theta. Then we make that substitution in the first term of our overall total wave, and that becomes k over 2 d sine theta. Now let's substitute for k. We remember that k is the wave number, 2 pi over the wavelength, and we simplify one more time and get this in a form where we can see clearly that this cosine term, which is part of the amplitude function, depends, of course it depends on constants like the separation between the slits and the wavelength of light, but most importantly it depends on the position on the screen through the angle theta. So we consider that an amplitude that depends on the angle theta, that whole term. So what we will do on the next screen is write down an expression for the intensity at that point. And we're going to use the definition that intensity is always proportional to the square of the amplitude. Because remember, amplitude in this sense can be both positive and negative. But intensity or brightness is something that we always experience as positive. So we define that to be a quantity that's proportional to the square of the amplitude. As a result, then, we can say that the intensity at an angle theta on the screen is proportional to the square of the amplitude at that point. And the proportionality constant, we don't know what that is, but we know that this proportionality holds. And so just to remind you where that came from, all we did was take this term, the 2a cosine term, and we squared it to get this expression here. Now, what we're also going to do is make use of the fact that the intensity from a single source, we'll call that I0, that's proportional to the square of the amplitude of a single source, which is just a. That would be a source where the traveling wave is just a times the cosine of kx minus omega t. So we can write that proportionality down as saying the intensity for a single source is just proportional to the amplitude squared, and these proportionalities must have the same proportionality constant, right? Because both of them tell us that the intensity is proportional to the amplitude squared. So whatever the proportionality constant is, since it's the same in those two equations, we can just divide them by each other, which cancels out the proportionality constant. So I at position theta divided by I0 is equal to this term up here, the 4a squared cosine squared term, divided by a squared. And so finally the a squareds drop out, and we're left with a very simple answer for the intensity of light at a position on the screen given by the angle theta. And we can see that this intensity is made up of a term out in front, which, notice, this is 4 times the intensity of a single source. And then the cosine squared term will oscillate back and forth from 0, which is what we would get at certain values of theta, to 1 at other values of theta, and so on. So this assumes, the one assumption that we have made is that, and we stated this up here, is that a single slit gives a uniform intensity I0 at all points across the screen. And that's a very good approximation if that slit is extremely narrow. We'll consider a little bit later on the case if that slit has a width to it. But for now we'll just assume that these slits are very, very narrow slits. So what does that function look like? Like I said, at theta equals 0, here we're plotting intensity versus sine theta. To keep it simple, and at theta equals 0, that means sine theta is equal to 0, and the intensity will have its maximum value of 4I0. And then when the angle gets a little bit larger, it goes down to a minimum, and then back up to a maximum, and so on. And on a viewing screen, what we see, we don't see obviously this kind of plot, but what we see is where the peaks in the plot are, that's the center of the bright fringes. And then where the troughs are, where the zeros are, that's the center of the dark fringe that's adjacent. So I've lined these two up so that the peaks are at the same positions as the centers of the bright fringes. And one of the things that we often will see, although in this viewing screen image it looks like the bright regions and the dark regions are roughly the same width, what you'll see if you look at it with your own eyes as opposed to taking a camera image, you'll see that the bright fringes are wider than the dark fringes. And that's simply because your eyes are really, really sensitive light detectors. And so if you can detect intensities way down low on this plot, and if I drew a horizontal line way down low near the horizontal axis, you'd be able to see that the width of the bright region, where you actually can see light, is going to get larger, and the widths of the dark regions are going to get smaller. So this is a quantitative treatment of the intensity as a function of position on the screen. Now we're going to move on and consider a separate phenomenon, which is another manifestation of the wave property of light, although this is a phenomenon that happens for all kinds of waves, and it's called diffraction. And in particular, we're going to look at diffraction of waves when they pass through a slit or an aperture. So diffraction refers to the bending of a wave when it either passes through an aperture or when it encounters an object and has to pass around that object. So we already should be familiar with this kind of a phenomenon in the case of water waves or sound waves. And here's an overhead view of a water tank where a ripple is created by a wave coming in from the left and encountering this obstacle that has a very small opening in the middle. So this aperture then, as the plane waves come in, these are waves that are created by, let's say, taking a stick and splashing it into the water at regular intervals, so that you get this wave propagating from left to right, and then it encounters this solid barrier so that none of the wave passes through at the barrier, but only through this central slit. But notice what happens. After it passes through the slit, part of the wave bends around the corners of the slit. And so we end up with that slit looking like a point source of waves. And so if that slit is really, really narrow, it really does act like a point source, and that would tell us that the intensity of waves on a distant screen or wall would be pretty much the same all the way across. So that's the approximation that we were making just a few minutes ago when we analyzed the intensity of the double slit experiment. So waves, when they pass through an aperture like this, some of the wave travels around the corners, and so there's a bending phenomenon going on. And this is very interesting because it says that as opposed to, let's say, a stream of particles, if you had this being a stream of particles, you would imagine they would either go through the slit and travel in a straight line path, or they would hit the barrier and they wouldn't go through the slit at all. So if this were instead a stream of particles, we would expect to just see a clump of particles hitting the screen on the right near the original trajectory that came through the aperture. But when we have waves instead, we get wave phenomena where there's bending around the corners of the aperture. Now, what about light? Does this happen for light? This was one of the difficulties in the early days, back in the 17th century. People realized that if light were really a wave, that it should exhibit this kind of bending phenomenon. But they had no idea what the wavelength was, and didn't realize that in order to see this for light, because light has such a small wavelength, you'll need to have an aperture that's very, very thin, or very, very narrow. So let's consider this setup and just schematically show what happens when we do this experiment with light. Here it's only passing through a single slit, and we use the letter A to indicate the width of the slit. When we look at the pattern on a distant screen, we see something interesting. We again see a series of bright and dark fringes, or bright and dark regions on the screen, like we did with the double slit experiment, but with a couple of qualitative differences. What we see is the central bright region right here, which is centered on the horizontal dotted line. It's actually quite a bit wider than the other bright regions. And when we look at this in class, I'll be able to show you a demonstration. You'll see that that central bright region has most of the intensity of the overall pattern. These subsequent bright fringes get dimmer and dimmer as you move away from the center. Nevertheless, there still is this series of bright and dark fringes. And once again, the only way to make sense out of this is to think of the light as having a wave-like character, so that in some sense there must be constructive and destructive interference happening at different points on the viewing screen. But this is a little bit odd, because when we think of light going through a single slit, it makes it seem like there's only one source. And if you've only got one source of waves, how do you have interference? Well, let's take a look at that on the next slide. How can this be? If we've only got one source, we would expect to see, a little bit like the photograph that I showed a few minutes ago, that we would just see a rippling effect of the waves coming through the slit. And it wouldn't predict that there would be maxima and minima, or interference, bright and dark regions. So what's happening? Well, imagine that we take the slit and divide it in half. So if the slit is centered on this dotted line, there's a top half and a bottom half to it. And now imagine that you've got a point in the top half and a point in the bottom half that are separated by a distance a over 2. Well, the light traveling through, coming from those 2 points, we can think of the light passing through those 2 points as making up separate sources. And so if that's true, then light that passes through the upper dot and then reaches the screen at a certain point, and light that passes through the region where the lower dot is and reaches a point on the screen, that light could, under the right conditions, interfere constructively or destructively at different angles theta on the screen. So if we realize that this single slit is actually composed of infinitesimally tiny individual sources, then we see how constructive and destructive interference could happen. So let's analyze this situation and write down the conditions for the dark fringes. Okay, so if we take these 2 dots that are separated by a distance a over 2, because we've cut the slit in half, the path difference, delta x, is this additional distance here, which at an angle theta is going to be equal to a over 2 sine of theta. Remember, that comes from the analysis of this right triangle that's set up when we make the perpendicular line here from the top dot to the line joining the bottom dot and the point on the screen. So that path difference is a over 2 sine theta, and for destructive interference, that path difference should be a half integer multiple of the wavelength. So we've listed a few of the first 3 values here. If we use that and multiply both sides by 2, we see that a sine theta is lambda, 3 lambda, 5 lambda, so all of the odd multiples of wavelength. And it's tempting to think that maybe that's the end of the story, because if these 2 dots light coming from these 2 points interferes destructively, then if we just shift down to 2 points immediately below these, they would still be separated by a distance a over 2. So all of the different points in the slit could be paired up like this, and this would tell us at the right value of theta we would get destructive interference. But this is not the end of the story. Oh, let's take a quick look again. Here's a schematic diagram of the slit expanded a little bit, imagining that we subdivide it into many, many, many tiny dots. The point is that if we break the slit in half, we can always pair up these dots into pairs that are separated by a over 2. So that condition for destructive interference will apply to all pairs of dots that make up the entire slit. Okay, but that's not the end of the story, because it might have occurred to you that you could also divide the slit up into quarters instead of halves, and then you could divide them up into eighths and sixteenths and so on. And the mathematics for each of those choices would give us slightly different expressions for the path length. So for halves, this is what we already did. We realized that if you divide the slit up into halves, that produces pairs of points that are separated by a distance a over 2. So the path difference is a over 2 sine theta. But for quarters, I'm not going to draw a diagram, but if you divide the slit up into quarters, then you create pairs of points that are separated by a distance a over 4. So that the path difference, a over 4 sine theta, if that's still equal to a half integer multiple of the wavelength, and we multiply both sides of this equation by 4, now we see we're generating additional solutions, additional values of a sine theta that produce destructive interference. So now this gives us lambda, 2 lambda, 3 lambda, 5 lambda, 6 lambda, 7 lambda, 9 lambda, 10 lambda, so on. Is that all we have? No, because you can do the same thing with eighths. You can divide the slit up into eighths. So now we get, for the path difference, a over 8 sine theta. Setting that quantity equal to a half integer multiple of the wavelength gives us a sine theta is 4 lambda, or 12 lambda, or 20 lambda. So now, if you look at these, we've got 1, 2, 3, 4, 5, 6, and 7, right? You get the idea. What happens if you go on and repeat this process with 16ths and 32nds and 64ths is you end up generating all of the possible integer multiples of a wavelength on the right hand side. So the general equation, remember this is the equation for the dark regions, for the intensity minima, is given by a sine theta equals m lambda, where m is any non-zero integer. The reason m can't be 0 in this equation is because this is the equation for the dark spots. M equals 0 would correspond to theta equals 0, and we know at the very center of the screen that's where there's the bright region, right? So don't make the mistake of plugging m equals 0 into this equation, because that would not be consistent. So let's do a quick example just to show how this works. Find the width of the central maximum diffraction peak for light of wavelength 633 nanometers illuminating a 1 millimeter slit on a screen 4 meters away. So always have to draw a sketch to illustrate this. We've got the single slit. There is a point on the screen over here. The screen is a distance L away. And what we want to do, in order to find the width of the central maximum peak, we would like to find the distance on the screen between the first minimum on the top of the pattern and the first intensity minimum on the bottom of the pattern. So if we can find this distance y1 using some geometry, then double it, that will give us the width of that central bright region. Okay, so it's simple enough to use the condition for where a minimum is located. A times the sine of theta 1 is just, using m equals 1, it's just going to be lambda. But to get y, we're going to use an expression for the tangent of theta, because that's going to give us the correct relationship. So this will allow us to solve for the angle. We know the wavelength, we know the slit width, So we find the angle is very small, 0.036 degrees. Now, from the geometry of the sketch, that y distance is L times tan theta 1, which gives us about 2.5 millimeters here. When we double that, we get just over 5 millimeters, which is the distance between the first minimum on top and the first minimum on the bottom. So that's something that we actually could make a measurement of on the screen and compare that to the predicted value if we knew the value of A and if we knew the value of L, and of course the wavelength. So I hope that's helpful. That's very similar to a homework problem that you'll have to do, and I will see you in class.